Okay, so we finished looking at all of the Amplify questions. So now we are looking at final exam review. So I'm going to be recording all of my classes, all my pre-cal sections doing the final exam review, and I will post those on YouTube. So some of the recordings, when I'm doing it in different sections, I'll end up repeating some of the questions. Um, I'm just posting the recordings so that way they're there if you wanted to look at them. So let's see. So our practice final exam is the final exam practice problems. There's 20 questions in there. And it's a really good match for what is going to be on the final. So let's open it up with anyone who's taken a look at those problems. Is there a particular problem you want me to start with? All right, let's take a look. Yeah, 14's got some ugly numbers. All right, so 14 here, they tell us to find the formula for an exponential function of the form y equals a times b to the x, and they give us the 2 points on the function. Now, neither of the points is the 0 point, so they're not giving us the initial value. So this one is going to require a little more work than what is on the final, but like this style of question where you're given 2 points and you have to figure it out is going to be on there. So it's a good one to work from. All right, so 1 point is -3 comma -1536 over 343. And then the other point is -1 comma -24/7. All right, so first thing is just plugging these numbers into the formula. There's calculator. All right, so I have to take one of these formulas and solve for a variable and plug it into the other one. So the b to the -1 here, that power is a little smaller, so I'm going to rewrite this. That'll be a times 1 over b. So to get a by itself, I need to get rid of 1 over b. Now, since it's a times 1 over b, I can divide by 1 over b, but dividing by a fraction is the same as multiplying by the reciprocal. So I can multiply by b over 1 on both sides. So this will leave me with a by itself is -24b over 7. Right, so the b times b to the negative third, that is b to the first times b to the negative third. There's a extra b there, so these are not close enough to multiply, so I'm going to add those exponents. So 1 plus negative 3 will be b to the negative 2. And then I still have all the other crazy numbers. So to start getting b by itself, I got to get rid of that negative 24/7. That is being multiplied to the b to the negative 2. So I'm going to multiply by the reciprocal, so 7 over negative 24. And this fraction looks really ugly, these two fractions I'm multiplying, but they will actually work out to be a nice fraction. So like, even though the calculator originally is like, here's an ugly decimal. Yeah, that's nice. Give me the fraction. So the 7 goes into 343 49 times. The 24 goes into the 1536 a nice number of times. Now on the test, it'll be an ugly number, and that's that. But for web work, this actually will work out to be a fraction answer. Now b to the negative 2, I need to cancel out the negative 2 power. So I can only do this using another power. I need a negative power, so that negative times negative will be positive. And then to get rid of 2, because I'm trying to turn this into b to the first, I need a 1/2. So now I've got my 64/49. I put that in parentheses. And then I raise that to the negative 1 divided by 2 power. And this spits out a fraction answer of 7/8. So I have my b value. Now I need to take this back over here to figure out the a value. And this actually ends up being -3 for the a value. So our final function formula, or y equals, because they did say y on this one, will be -3 times 7/8 to the x power. They already typed the y equals, so all you'll have to type in is the formula part. Um, so some of them are going to be very similar to the test questions. It's more likely to be like the test than it is like web work, but there are questions that from this last chapter, so they haven't been on an exam, but they are going to be on there. So like this question, you are going to be given 2 points and you have to find the function formula, but the numbers won't work out to be a pretty fraction. The b value is an ugly decimal. But then it asks a follow-up question of, now that you have this function formula, like predict what's going to happen in this new time frame. Because it's an actual word problem, but we give you the explicit points in it. So that one will be closer to the writing assignment, question 4 from the one that was due at the beginning of this week. All right, what's another one we can take a look at? Yep. All right, so number 9 tells us tangent is 2, tangent of theta is 2, and theta is between 0 and pi over 2. And then they tell us to use the double angle identities to find the exact values. All right, so on the test, it won't be a quadrant 1 angle. But in webwork, like all of the double angle questions, they kept making it a quadrant 1 angle. I didn't have a question where it wasn't quadrant 1, so that part's a little annoying. But the initial setup is the same. So we know tangent of theta is 2. And I'm going to sneak in the over 1 there, because we're going to use this to draw a triangle. Now, since they told us we're in quadrant 1, I draw a quadrant 1 triangle. There's my theta. So tangent is tripping on acid, opposite over adjacent. Opposite is the vertical side. Adjacent is the horizontal side. So I need to figure out my hypotenuse. So I'm going to call that hypotenuse C. So Pythagorean theorem, 1 squared plus 2 squared equals C squared. So I end up with 1 plus 4, which is 5. Now I did a square root, so I have that plus or minus question, but the hypotenuse is always positive. So our C value there is the positive square root of 5. So I figured out the third side of the triangle. So I can state what the sine of theta and the cosine of theta are. So sine of theta, opposite 2 over hypotenuse square root of 5. And cosine of theta is 1 over the square root of 5. Now, if this was in some other quadrant, some of those would be negative or both of them. But since we're in quadrant 1, everything's positive. Now, to answer our sine 2 theta and our cosine 2 theta, we would go look up the formulas for these. So the sine of 2 theta is 2 sine theta cosine theta. But I know what sine and cosine theta are now. I just figured them out. So I'm just going to fill those in. And we actually end up with 2 times 2 times 1 on top, which is 4. And square root of 5 times square root of 5 on the bottom is 5. So our sine 2 theta is 4/5. Now our cosine 2 theta formula has 3 different formulas, but I usually go with the first one just because I'm lazy. So cosine squared theta minus sine squared theta. So cosine is 1 over the square root of 5, cosine of theta. So I have 1 over the square root of 5 squared minus, and then my sine theta is 2 over the square root of 5. But the formula also says to square that. Now, this is all numbers, so you can punch it up on the calculator. But this one will be 1/5 minus 4/5, which gives us negative 3/5 for cosine 2 theta. So theta was in quadrant 1, but when we double theta, this theta ended up in quadrant 2. So that's why our cosine is negative. But the formula itself took care of that for us. So we didn't actually have to figure out what theta was to figure out if 2 theta was still in quadrant 1 or if it was over in quadrant 2. The formulas did that part for us. Now in the test, it's only going to ask one of them. I don't remember if it's sine 2 theta or cosine 2 theta, but the formulas for both of them are going to be provided. All right, what's another one we can take a look at? All right, so 4 is a nice little word problem. And I only call it nice because it's little. So not a lot of words, not a lot of translation we got to do. So we have a 20-foot tall ladder leaning against a building so that the angle between the ground and the ladder is 84 degrees. How high does the ladder reach up the side of the building, round to the nearest hundredth? All right, so let's draw a picture. So we got our ground. Got our building. We got our ladder. And they told us the ladder is 20 feet long. All right, then they say the angle between the ground and the ladder. So the ground and the ladder is this angle here. That is 84 degrees. And then the question was, how high does the ladder reach up the side of the building? So up the side of the building, that's this side over here. Now we know, even though my drawing is bad, buildings meet the ground in a right angle. So we have a right triangle in there. So if we have a right triangle, SOHCAHTOA can be used. So I need to label these sides relative to the 84 degrees. So my 20 feet, what side is that? Is that my opposite, my adjacent, or my hypotenuse? Yep, because that is directly across from the 90 degrees. Now the side that I'm looking for, is that opposite or adjacent? Yep, that is across from the 84, so this is the opposite side. So I know my hypotenuse, I want to know my opposite side, so I want the trig function that uses O and H. So that's our some old hippie, there it is, but caught another hippie tripping on acid. So sine of theta is opposite over hypotenuse. And now I'm going to fill in the pieces I know. I know the angle is 84 degrees. My opposite side is my unknown, so I'll just, I don't know, I guess I'll put a Y there since it's vertical. Over, and then my hypotenuse is 20. So now I have an equation with only one unknown. I can solve for Y. Since Y is being divided by 20, I will multiply by 20 on both sides. And now we just got to type that on the calculator. Now make sure your calculator is in the right mode. That's 84 degrees, so we need to make sure we're in degrees mode. On the final exam, you're going to have to flip your calculator mode several times. So like any question where you pick up the calculator and you start typing trig buttons, like always double check, am I in the right mode? So 20 sine 84. This spits out 19.8904, blah, blah, blah. Round to the nearest hundredth, so 19.89. So that's almost 20 feet. But 84 degrees is actually a pretty big angle. So this ladder is almost vertical. It's really, really close to that wall. So as long as you remember your right triangle setup and your SOHCAHTOA, your hippies, and how to solve the equation, like this one's actually pretty short and straightforward. So some of the questions on the final are this short. Like some of them you're not going to have a whole lot of work once you realize what you're doing. All right, what's another one we can look at? 13, the polar one. So we do have one polar coordinate question on the final, but it is multiple choice. So you can work it either direction you want. So on the test, we're going to give you an XY point, and we ask for the equivalent polar point. But you can also take the polar points, convert them into an XY point, and see which one matches. Or you can just kind of think about where the point is and reason through which one is actually in the correct quadrant as well. So a couple of ways to actually approach this one on the final. For what webwork is asking, they've given us a whole bunch of polar points, and they're asking which is the rectangular point. So remember, our polar equations, x equals r cosine theta, and y equals r sine theta. All of my first list here, these are all r theta points. So since I know r and theta, I can plug those in and get my x and y directly, and the results I get are the answers. Like there's no ambiguity when you're going in this direction. So let's just go with the first one then. So the x coordinate is going to be 8 cosine negative 6 pi over 2. And then the y is going to be 8 sine negative 6 pi over 2. Now, since we've got pi numbers for our angles, we need to put the calculator in radians mode. Now I can type it in, 8 cosine negative 6 pi divided by 2, and that spits out negative 8 for the x. And then my y, 8 sine negative 6 pi over 2, spits out a 0. There it is for B. Now, on the final exam, it's just a singular point and you're picking between the multiple choice answers. So it's not matching 6 different points. So the amount, this question takes longer because you got 6 points to work with, but on the exam, it's much shorter because it's just the 1 point you're working from. I think it's about half and half. So I think it's like 9 are multiple choice and 8 are free response. But some of the free response are like really short, like this one we just did with the ladder, that one's a free response. So you just get your number at the end, done. So yeah, not all the free response are super long. It depends on the question. So like this one, all of the angles that we got here are radians, so we have to put the calculator in radians to do it. But the previous question, that was 84 degrees, so we had to put the calculator in degrees to crunch that one. So it depends on the questions you're working. I think more of them are in degrees than radians, but the ones that are in radians, like you'll see pi numbers. All right, what's another one we can look at? So 8 looks like really gross looking. And it's doing the whole like, which of these are equivalent? So you can have more than one answer, which is annoying. This one is one of the multiple choice ones on the final, but the angle I pick actually makes the thing work out. Like it simplifies down really nicely. But on webwork, like it doesn't always pick a nice angle. So some of these work out weirdly. But the multiple choice on the test, only one of them will be correct. So it's not like this where it's, we have to consider each answer. Now this is a difference. So we would look up our sine, sum, and difference formula. So the sine of A minus B is sine A cosine B minus cosine A sine B. So when we're looking at sine of x minus 3 pi over 4, everywhere there's an A, I'm going to put an x. Everywhere there's a B, I'm going to put a 3 pi over 4. So I have sine x cosine 3 pi over 4 minus cosine x sine 3 pi over 4. Now, some of the answers are written in this format. So the first thing I like to do is like just double check, is this one of the answers? And like D is similar, but it's backwards. So that's enough to say, nope, not D. F, sine x cosine 3 pi over 4, but then they put a plus. So okay, not F. All right, now to figure out the rest of the answers, we actually have to evaluate the cosine and sine of 3 pi over 4. So our over 4 angles are always square root of 2 over 2. We just got to figure out if they're positive or negative. Now there is a full complete unit circle on the test on the front and on the back page that you can rip off. So the cosine of 3 pi over 4 is negative square root of 2 over 2. And the sine is positive square root of 2 over 2. Now, just to clean it up a little so it pattern matches, that negative, I can pull that out front. So it's negative sine x. And then I can write the square root of 2 over 2 in front as well. So negative square root of 2 over 2 sine x minus square root of 2 over 2 cosine x. All right, so it's definitely not A and B. Those are the wrong numbers. C, everything is positive, so it's not C. But E is correct. So you just copy down the right formula, follow the pattern, evaluate the ones that had numbers, and then simplify it a little and find the answer that matches. All right, what's another one in there we can solve? Yep, 11 is a good one. Now, I originally had a different question 11, and then I looked at the final and traded it out for this question 11. For random reasons. So this one, we've got 2 times the sine of 3 theta equals the square root of 3. So that 3 theta in there is going to be a little bit weird in our answers, but the first steps are still the same. We're just trying to get our theta by itself. So 2 times the sine of 3 theta is equal to the square root of 3. So first thing I'm going to do, like when I look at all the stuff here stuck onto the theta, there's a 3 right next to it. Then there's a sine outside of that. And then there's a 2 outside of that. So the first thing I'm going to get rid of is that 2. So square root of 3 over 2, that at least sounds familiar. So I have the sine of 3 theta equals the square root of 3 over 2. Now, sine is equal to square root of 3 over 2 at two particular places on the unit circle. So this is where I'm going to go look at my unit circle. So the sine is square root of 3 over 2 at pi over 3 and at 2 pi over 3. Because sine is positive in quadrant 1 and quadrant 2. Now, what I was taking the sine of was a 3 theta. So I have 3 theta equals these two angles. But also, when I pull from the unit circle, this is also where the 2 pi k shows up and when the 2 pi k shows up. So when you pull angles from the unit circle, you're also saying everybody coterminal with that angle is also an acceptable solution. All right, now 3 theta is equal to this. Now I can get rid of that 3. Since that's being multiplied to the theta, I'm going to divide by 3. Dividing by 3, though, is the same as multiplying by 1/3. So this 1/3 is going to distribute into both parts. So now I finally have theta by itself. I have pi over 9 plus 2 pi over 3k. And then I also have 2 pi over 9 plus 2 pi over 3k. Now, this question is not multiple choice. You are going to have to work it out and wrestle with the k values. But we've got our general solution. So if you can get to here, that's worth most of the points. So now to produce our list of answers, we have to pick k values. Now, since it was a 3 theta, we're going to choose 3 k values. We're going to start with k equals 0. And then we're going to do k equals 1 and k equals 2. So we have 3 total k values. So with k equals 0, I get the pi over 9 plus 2 pi over 3 times 0. So I just get pi over 9. And then for my other one, I'm going to get 2 pi over 9. So there's my first two solutions. Now my next k value, now I'm going to actually have some fractions to work with. So I have pi over 9 plus 2 pi over 3 times 1. And this calculator doesn't like pi's, so 1/9 plus 2/3, 7/9. So 7 pi over 9. And then this one over here, 2 pi over 9 plus 2 pi over 3 times 1. So 2 plus 6 will be 8 pi over 9. And then we just got to do one more. K equals 2. The pi over 9 plus 2 pi over 3 times 2 So that'll be 13 pi over 9. Fourteen pi over 9. So we ended up with 6 answers. Go for it. So we picked 3K values, 0, 1, and 2, because we originally had 3 theta. So whenever what's inside the trig function is more than just a single theta, you're going to have to pick K values. I always start with K equals 0, because that gives me like easy numbers to work with. And then I just go however many K values that number inside told me. If I did K equals 3 and I plugged 3 into the formula, the result would actually be bigger than 2 pi. So it's not part of my solution list. It is technically a solution to the problem. It's just not between 0 and 2 pi, which is the added qualification that the problem gave us. So that's why we're getting a finite list of numbers instead of the 2 general solutions. Now, how did I get the other pi numbers? So pi over 9 plus 2 pi over 3, I need a common denominator to add those. So we can also think of this as 1/9 plus 2/3. 2/3, I'd multiply it by 3 over 3. So I end up with 6/9. So 6/9 plus 1/9 is 7/9. So 7 pi over 9. But you can also, like, if you don't like doing the fraction math in your head, just like ignore the pi's, know that you're going to have a pi in your answer. And so then this would be 1/9 plus 2/3, and you can type that on the calculator, tell the calculator to spit out a fraction, and it'll spit out the 7/9 for you. Now it won't be 3 theta on the test because that's just like a little bit of extra work for no extra reason. But you are still going to have to mess with the K values some. Let's take a look at 10 just for comparison's sake, because that's the other trig equation to solve. So this one does not have an extra number with the theta, but it is a quadratic. So we can get like everything on the same side and try to factor this. Or since it's only a single trig expression, I can get that trig expression by itself and use the square root property to solve here. So it does sort of factor. I don't remember if this one works out to be a fraction or a square rooty answer. But usually when I only have the singular trig expression, I just go with the square root property. All right, so our first step is to try to get the cosine squared theta by itself. So I've got an 8 being multiplied, and I've got a 5 being added. So I can deal with those in either order, but usually we deal with the addition or subtraction first. So 8 cosine squared theta equals 2. And then I divide by the 8. So cosine squared theta equals 1/4. Now, how do I get rid of the square? Yep. So we're going to square root both sides, but what else do we have to remember with square roots? Yep, and the plus or minus is what most people missed on exam 3 on this one. So this will now be just cosine theta by itself equals plus or minus the square root of 1/4 is 1/2. So we did a fair amount of work. Our trig expression is finally by itself, no exponent. So this is the step where we go to the unit circle. Now, because of the plus or minus, we're actually going to end up with 4 answers. So we're going to get 2 answers from where cosine theta is positive 1/2, and 2 answers from where cosine theta is negative 1/2. Now, all the angles are going to have the same denominator because we're supposed to answer in radians. So let's see, cosine is 1/2 at pi over 3. And then cosine is positive in quadrant 4, so this other angle would be 5 pi over 3. And then cosine is negative 1/2 at the other over 3 angles, which is 2 pi over 3 and 4 pi over 3. So all 4 of those are the answer. And you should just be able to type them in any order. When the thing inside the trig function is only a theta. Like I could technically write on each of these, I could put plus 2 pi k. Yeah, we plug in 0 and just get those numbers. If we plugged in 1, they'd be too big. If we plugged in -1, they'd be negative. So, like technically the 2 pi k should be there. It's just not part of our final answer. So if you don't write it in your work, like you're not going to lose anything. So the k value part like takes a little bit extra on here, but you're only going to have to deal with 2 k values. Like anything more than that is just extra busy work. So it's too long for the test. And then the quadratic, we had more than 2 answers as well because of the plus or minus from the square root. If we factored, we would get positive 1/2 and negative 1/2 from the factors. All right, what's another one we can look at? What about some of those log equations? That's 19 and 20. They're both very similar. Like the only difference is on 20, you move the log to the other side, and then it's just like 19. So looking at this equation, I've got multiple logarithms equal to some number. In order to solve this equation, to start getting x by itself, I need the logarithms to be smushed and combined into a single logarithm. Now remember, logarithms do the crazy thing where they actually change an operation. So here I've got two separate logarithms being added. So if I use my log property backwards, then when I had the two different logs being added, that came from a single log with the insides being multiplied. So the logarithm changed multiplication into addition with two separate logs. So when I work it backwards, the addition goes back to the multiplication, and now it's a single logarithm, still equal to the 1. So the log property we use there, that you're going to have to remember. I'm not going to write the log properties on the test. All right, now that it's a single log expression, now I can use my inverse operations to get rid of log base 10. So what do we use to cancel out log base 10? So what's our base on the log base 10? 10. So our natural log, what's our base on natural log? E. So both of those are logarithms just with different bases. So those guys don't undo each other. They're just our two most common logarithms. Yep, so this is the exponential, the 10 to the power on both sides. So like log and natural log are often covered together and they kind of like stick in your head together, but they're not inverses of each other. They're just two different logs that show up a lot. So now I have x times x plus 3 is equal to 10. All right, so I'll get rid of my parentheses by distributing. So x squared plus 3x equals 10. Now I've got a quadratic. I only solve quadratics when they're equal to 0. So I need to minus the 10. So I have x squared plus 3x minus 10 is equal to 0. So this does factor. And there's not a lot of options. So we get the x times x. 10, it's either 1 times 10 or 2 times 5. 1 and 10 are too far apart. They're never going to add or subtract to 3. So it is going to be the 2 and the 5. Now I want to get positive 3x. So I want to make the 5 positive and the 2 negative. So that way I'd get 5x on the outside and negative 2x on the inside. 5x minus 2x is 3x. Now you can also use the quadratic formula and that'll get you the same results. It'll take a little bit longer, but if you're just like, you get really flustered by factoring, quadratic formula is always an alternative. And if you get really good at it, it doesn't take that much longer. So the x minus 2 is equal to 0, or the x plus 5 is equal to 0. So we get 2 and negative 5 as potential solutions. Now on a log equation, you want to check your result, and what you're looking for is a domain violation. So I'm going to check x equals 2 back into the original equation. So that'd be log base 10 of 2 plus log base 10 of 2 plus 3 equals 1. Log base 10 of 2, I can type on the calculator, that's a number. Log base 10 of 5 is a number. So x equals 2 is a viable solution. The x equals -5, though, when I start to write the equation, log base 10 of -5, wah, wah, I can't take the log of a negative number. So that is enough to throw out -5 rather, as a solution. We cannot use that as a viable solution. So 2 would be our only solution here. Now, in class on Tuesday, we covered this one a little bit differently because we talked about the domain restriction at first, and you can do it from that perspective. And then we'd see that 2 works and -5 is too negative. But if you don't remember to do the domain restriction at the beginning, you could do it at the end and check your answers against it. Or you can just plug the numbers back into the original equation and see if they give you bad math. So see if they give you a negative number inside the logarithm. And usually it'll end up being like a negative number in both of the logarithms. Like if I finish this, log base 10 of -5 plus 3, that's log base 10 of -2. Also negative, also a problem. Can't log negative numbers. So that's why I'm throwing out -5. Not because it's negative in itself, but because when I plug it back in, it's putting negative results in the logarithms. Like we saw at the end of class on Tuesday, we had a solution of -2 that worked in the equation because the equation had a minus sign with the x, so the negative numbers actually worked. So it's not just that we always throw out negative numbers, we always have to check it back against the original equation because it is completely dependent on the structure of the original equation for what works. All right, what's another one you guys want to look at? So the graphing part won't be, but another part of 15 will be. So here, let me grab that one. It's just 15 is the only one that I had that asked about the domain of a logarithm. So it has some graphs, but the graph part won't be on the test. So the only part you'll actually have to do for the test is the domain. This is 15. So when we're looking for the domain, very often we start with the vertical asymptote. So the vertical asymptote is the number that makes the inside of the logarithm 0. So I set x minus 4 equal to 0, which gives me x equals 4. That is the vertical asymptote. So when I'm thinking about the graph of this particular function, It's got an asymptote at 4. So my log graph is either going to be completely on the left of this asymptote or completely on the right of this asymptote. But I have to figure out which one it is. So the -4, x minus 4 shifted the graph right 4. And then the +1 there shifts the graph up 1. And then this minus sign in front is going to do a flip. But we have to figure out which way that flip goes. So since this flip is outside the function, it's going to flip our y values. So this is going to flip positive and negative y values. So positive y values are on top, negative y values are on the bottom. So this is a up-down flip or a vertical flip. I don't like using the words horizontal and vertical because we're flipping the graph vertically, but we're flipping it across a horizontal line. So I hate the words vertical and horizontal because they both have a context here. So that's why I use my weird words for up down is flip the top and the bottom. So then I know I'm doing my flip the right way, or left right is left and right side. So an up down flip is just going to turn my graph over, but it's not going to flip it across the asymptote. So my original log graph is on the right side of the asymptote. When I move it right 4 and up 1, it's still on the right side of the asymptote. And then when I flip it up down, it'll be a decreasing log graph. But it's going to be on the right side of the domain restriction. So our domain is from 4 to positive infinity. But the other way we can get that is to just say whatever is inside the logarithm is strictly greater than 0. And I end up with the inequality x is greater than 4. So this is the other way to see that, oh, my points should be on the right side of the asymptote. If x is greater than 4, then that is all my numbers to the right of 4 up to infinity. And log domains always have parentheses because we're never going to actually equal the asymptote value. So this is going to look a little weird, but like here is what the original just like log base 4 of x would look like. It's got its asymptote at x equals 0. So then I'm going to shift it right 4. And then I'm going to shift it up 1. And then I do the up-down flip. So my asymptote will still be at 4. But that flip number will actually be like, it goes from up there to down here. So it'll be like that. So I took all four of the transformations that the equation had and just applied them in an order. Like knowing the order comes from practicing with these problems, but usually you do it from the inside out. I could be wrong. It could actually go through that point up there. I don't remember exactly where that point ends up. But it is for sure on the right side of the graph. Like if we wanted to know for sure, I could plug in the number 5 into the equation. So negative log base 4 of x minus 4 plus 1. So I'm going to figure out what f of 5 is. Negative log base 4 of 5 minus 4 plus 1. So 5 minus 4 is 1. Log base 4 of 1 is 0. So negative of 0 is still 0. So this ends up being 1. So I was actually wrong. This graph is not there. It would be up here. Now, I don't think webwork actually makes you choose between those two, but maybe. Oh, no, it does. So yeah, it would be the C graph instead of the D graph. So I picked 5 because 5 is 1 unit to the right of the asymptote. And I knew the 5, like 1 unit to the right of the asymptote inside the logarithm, works out to be an integer. So I knew this 5 was going to give me a nice ordered pair. So it's telling me the point 5, 1 is a point on this graph. So when I look at the two graphs on webwork, one of them will cleanly go through 5, 1, and the other one goes through 5, -1. So the multiple choice, like as long as you pick the right answer, you get full credit on the multiple choice. If you pick the wrong answer and you show me work, then I can give you some partial credit, like half credit, as long as your work was like going in the right direction. But if you just like randomly pick the correct answer, you get full credit because some of the questions, there's not really work to show. Like you can totally do it without, yeah, and you'll still get full credit. Like this one, all it is they give you an equation and we ask for the domain and it's multiple choice. So you can look at, oh, x minus 4 is greater than 0, x is greater than 4, 4 to infinity, there's the answer. And you don't have to write anything and you did a full complete thought process. It made sense, it was logical. Yeah. So I'm not going to take off points if you don't do work unless you got it wrong. Mhm. I can try to do that, yes. I have to like go back and like find all the numbers I did and then remember to put it in there. I will try to do that because I know that would make like looking later a lot more sense. All right, we only got 3 minutes left, so that's not really enough time for a problem, but make sure to go through the review on Tuesday to bring up any extra questions you want to make sure I hit.